Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're going over a math problem that absolutely blew my mind. This has been going around on the internet a little bit. I've seen it in a couple places, but what I would call the Tuesday birthday boy problem. And here's the depiction of the problem statement. Mary has two children. She tells you that one is a boy born on Tuesday. What's the probability that the other child is a girl? Generally, you'd think, well, the answer's got to be 50%, right? Under the simplifying assumptions that there's a 50% chance that any given child is a boy and a 50% chance that any given child is a girl. And here he's claiming it's 66.6%, or 2 out of 3. And some people would look at this and say, yes, that makes sense for some probabilistic reason that we'll get into in a moment. And then someone else is saying, actually, it's 51.8%, which seems completely out of nowhere. Just bear with me on this. This guy in the black shirt is actually right under those assumptions. Now, a lot of people, when they see this, just assume, including the first time I saw that, I just assumed that 51.8% is the probability of a random child being male, which is kind of flipped from how it is, but I thought that's what it was referencing, because if you look worldwide, there are slightly more male children born than female children born. That's actually not what this is about. But let's get into this, and what I'll say is, right now it's saying she tells you that one is a boy born on Tuesday. We'll simplify that assumption a little bit, but at the very end, we'll get into just what the implications are on she tells you. So, if we ignore the Tuesday clause, right, suppose that you had large number of mothers in a room, and you say, if you do not have exactly 2 children, please leave the room. And suppose that after that happens, there are 100,000 mothers still in the room. Okay, big room. Maybe I should have said stadium rather than room. So you have 100,000 of them. Right? You would expect 25,000 to have 2 boys, 25,000 to have 2 girls, and then 25,000 whose first child is a boy and second child is a girl, and then 25,000 whose first child is a girl and second child is a boy. Right? By the way, this, adding on to the simplifying assumptions, assume that the child births are independent. Specifically, we're ignoring the possibility of having twins, because when you have twins, well, if they're identical twins and they're guaranteed to be the same gender, okay, fine. Under those assumptions, all right. Now, if we say you've got 100,000 in the room just based on having exactly 2 children, and if you say you may only stay if you have at least 1 son, any of your children is a son. Okay, so the 25,000 who had 2 girls would leave. And okay, now, if we were to ask, what of the mothers remaining, what percentage of them have a son and a daughter, right? That would be these 50,000 between these two, but not the 25,000 boy. And so that's where the 66.6%, or where the 2/3 comes from. Okay. Now, what in the world happens with how do you get 51.8%? Well, take a look at this. What if we then say, of those of you still in the room, only stay if at least one of your children is a boy who was born on a Tuesday. So now, if you had a boy and a girl, 6 times out of 7, that boy would not have been born on Tuesday. So 6/7 of them would leave. We're also assuming that you're equally likely to be born on any given day of the week. If you had 2 sons, you would only leave if both your sons were born not on Tuesday. So more of the mothers of 2 sons would remain. And when you crunch the numbers on that, you'd get 7,142 mothers of a son and a daughter relative to 13,774 mothers still in the room with at least 1 son born on Tuesday. That's where the 51.8% chance, or 51.85% chance comes from. That blew my mind. But it gets weirder. If we have another look at the problem, right, she just tells you one is a boy born on a Tuesday. Well, what if instead of phrasing it as, if you have at least 1 son born on a Tuesday, you may stay in the room, right? What if we say, okay, you have at least 1 son? Pick a day of the week that one of your sons was born on. Give the answer to, okay, if you didn't say Tuesday, leave. You can only say if you said Tuesday, which means if you have two sons, one of whom was born on a Tuesday and one of whom wasn't, and you chose the other son, then you'd have to leave anyway. So if you just ask, what day of the week was one of your sons born on? Pick one if you have multiple sons. Now, there's only a 1 in 7 chance that any given mother who was still in the room once you confirmed at least one son, right? 1 in 7 chance that anyone would say, and you'd get these equal quantities again, and it would go back to 2/3. So notice, the answer, whether it's 66 and 2/3% versus 51.85%, that depends a little bit on how the question was asked that led to the mother answering, I have a son who was born on a Tuesday. But it gets even weirder than that. Let's think about the assumptions we'd make about the conditions under which someone would say, I have a son who was born on a Tuesday. If you had two sons, how likely would you be to say, I have a son who was born on a Tuesday? Not, I have two sons, one of whom was born on a Tuesday. And so, if you had to assign probabilities to, given that you were in that situation, what's the likelihood that you'd say this? Right? Now you have to use what's called Bayes' theorem to try to go backwards with the probabilities and say, given that this is what you said, what's the likelihood that you had one son and one daughter? Really, we can't actually answer this question without knowing more about the context of the conditions under which you would say, I have a son who was born on a Tuesday. I hope you found this interesting. Until the next time, this is Dr. Nighttime wishing you a good night.